made it through the Oktoberfest crowd. Welcome to the Spectral Fitting Methods workshop, which is organized by Joern over there, Michael, and myself. If you have any questions during the workshop, talk to any of us. I will say a few words in the beginning, how local information, blah, blah, blah. Just to warm you up a little bit, this is all about analyzing spectra and counts. So this was all, anyone have a guess why there's a fish here? Poisson, right. So that's why there's fish here, about the Poisson distribution, we will talk about. Anyone know why there's a horse here? Now this is a little bit more difficult. The first application of the Poisson distribution in science or to an applied problem is horse kicks. So horse kicking the soldiers and deaths because of that, being counted by this guy. And then we will also talk a lot about this person developing the probability of data analysis and how to quantify hypotheses. And why there's a mouse, you have to ask Joern, he has a story about that. And now you might wonder, who are these people who developed the Poisson distribution? That was Dennerl. Who developed Bayesian inference? That was Laplace. And this person developing the horse kick application was Ladislaus. He was a Polish guy working in Germany. Now you might wonder, why are these things not named after the person who developed them? Well, that's Stigl's law of epinomy, which was developed by Merkel. Okay. So some practical information about the workshop. I already introduced the organizers. Wi-Fi access you have here. And I also tweeted that accidentally to the whole world. Then,
there's no change. This is the old one.
This is the old one, there's a new one?
Yeah, there is a new one completely new.
Cool.
There is
Right.
It's on the door.
There's a complete door on the door. The door is
Could you yell it to me? What's the new password?
Let's put it this way.
Also,
Who does not have EU work?
No.
It's something
Not everybody has the
E.
new.
It's two gas at MB.
You.
Capital zeta, EU, capital G. It's in the board after the workshop.
Yeah. And also the account name is different.
Okay.
It's a shame, I've been coming here for 20 years, but this is not the first time this password has been changed.
Yeah. But they did not change it because of the picture. It was by chance that at the same time. The system, entire system changed.
I feel less bad now. Right, so I'll tell you a little bit about local information. You might all know how to find your way in MPE, and this map is completely wrong because you didn't walk this way because it's locked. You walk that way. But we are here, here's MPE, and we'll probably have lunch in the canteen, or if you want better lunch, maybe you can find it outside the campus at the bakery, or there's some more options there, but basically just follow other people. So some overview of the agenda. In the morning, we'll talk about some overview how the measurement process works, what are the fundamentals. We'll have lunch around noon. In the afternoon, we'll talk about algorithms and how to do the fitting itself. And a lot of other topics that come with that. We will end, I don't know exactly when, but we'll have a dinner at 7 p.m. I'll tell you in a second where that is. But we also plan to have a lot of discussions because this is not a lecture series of some sort. This is about you asking questions and figuring out how things work. So we'll try to keep it interactive as well. And I would also like you to think about what practical problems you have, and maybe especially tomorrow we can have some time where you can ask about your specific scientific application, possibly also today. the goal of this workshop is to expose you to what methods exist out there, what people have tried, and what are the benefits and the drawbacks of these methods, and what you have to pay attention to when you try to apply these. So, at this point I've been talking a little bit too much, so maybe we can go through to warm you guys up a little bit, what you would like to, so maybe you can briefly state what's your name, which institute you're from, and what you would like to get out of this workshop. Maybe we start here.
Okay, Konrad Dennerl. I've been working for decades here at NTE and involved in the calibration and have dealing a lot of with the spectral fitting and whether what I'm doing is correct.
My name is Johannes. I'm almost as long here as Konrad, and I think that as he did many spectra in the past with Buchner and all these kinds of extreme instruments, and I'm just curious what the workshop is about. Is maybe there's something new and will refresh my mind of fitting spectra and so on.
My name is Francesco Bernardo. I work here at NTE, the Dennerl, and I hope to improve my knowledge about statistics here.
My name is Joern, and I work here at NTE, and I work with galaxy cluster spectra in my master thesis, and now working with images mostly, but we can also extend again to spectra for source detection, for example. That's why I want to refresh my knowledge.
Salvatore, working also at MD. Normally my work with the GN started from an X-ray, couple of X-ray sources. Whatever is happening before, I have noticed like it's true, and whatever I learned today and tomorrow is already something plus.
Hi, my name is Rina Baronelli. I work at MD with AGN in the X-ray. I'm really interested in refreshing a bit the statistics knowledge. It's always good for you.
Hi, my name is Martin Meyer. I'm a new PhD student here at MD. I've been working on supernova remnants, and I'm looking to fit one or the other spectrum, so I hope I will have a good statistical background for this workshop.
I'm working here at NTE in software developer on pipelines, data reduction. So I'm here to check that what I am developing is important.
I'm mostly interested in broadband SED fitting, so X-ray and optical together, but to include gamma rays and function.
Very good. So let's see if I have to say anything before I hand over to Joern. Yes, so the dinner today is at 7 p.m. It's at Richard-Strauss-Straße is the name of the metro station, but also bus stop. You can get there with the U6 to the Lindenstraße and then change to the bus 59, or you go on to Marienplatz and then take the U4 both to Richard-Strauss-Straße, and you get out here at this intersection and it's diagonally across. And it's called Vapiano. But I'm sure many of us will leave together so you can hang on to some group of people. And now we'll get started on the first block, which Joern will take away about the fundamentals so we understand what we rely on, what our assumptions are, and how the whole process works, which we will build up on afterwards. And I should also say that we structured the workshop in a way that we first focus on the analysis of point sources, mostly in the softer X-ray, so below 10 keV. And then at the later blocks, we kind of expand, understanding this part, we expand to other wavelengths, higher and lower, and extended sources and so forth. Okay, so let me switch to you.
Okay. Good, works. So, my name is Joern Wilms. I do X-rays, I'm sorry to say, or not. I'm with Wilms Observatory. I mainly work on X-ray binaries, AGN, and some diffuse stuff with interstellar medium and detectors and administration, mainly. So the idea of this presentation is essentially to bring you up to speed on the nomenclature of what we do in X-ray astronomy. So I will start really with some instrumental basics. They will be known probably to 60 or 70% of you here, but they might not be known to the rest of you. And for others, you might know specific things there, but might not know the terminology. At least that's generally my impression when I talk with colleagues. So this will be a very, some of you might be bored in some parts, check your email. Others might not, and please interrupt me where something is unclear. As also the others said before, where this is a workshop, so we have not a really set schedule and so on. If there is a real interest in something, we can dive in and then come back out of that again.
Will the transparencies
they will be made available, yes. So, first of all, right, why do we do X-ray astronomy? I think it's important to think about that. And Joern summarized this in one slide a few years ago when we were selling Athena. Right, and X-ray astronomy is the science of everything that's hot in the universe. And we want to study that. Now, we study this mainly by trying to get astrophysics out of the observations that we are doing with satellites. Okay? We are working with high energetic radiation from missions that are far above the atmosphere because the atmosphere absorbs X-rays up to energies in the 10 TeV range. And this fact that we're working with satellites with very preset detectors in an environment that is not the best to operate these detectors, and with detectors that are usually having that are having a very complex behavior, is what makes X-ray astronomy complicated. For example, to those of you who have more of an optical or even radio background. So that is why, before we talk about X-ray spectroscopy, we first have to think a little bit on how the photons arrive on the detector and how the detector works. Because it is not possible to do X-ray astronomy without understanding the detectors that we are using. The beauty of X-ray astronomy has been that since we are working with satellites, X-ray astronomy is so expensive that we as a field could afford the development of very good software that hides many of the things that I'm going to talk about here behind a few things called a response matrix, an auxiliary response matrix, and some background models or something like that. So in other words, it is possible to do X-ray astronomy without understanding the measuring process. But if you do so, the likelihood that you're getting a bloody nose somewhere, and they're not noticing many things, is very high. Right? This is also the reason why, as a field, X-ray astronomy is a little bit separate from other areas in astronomy. Right? We have a more complex data model. Our data are less easy to understand in some sense, because in other fields you can go farther before you realize that you have really the same problems and that you are really applying the same data model as we do in X-ray astronomy. But since the field historically comes from a different background, right? It doesn't come from X-ray astronomy, it doesn't come from optical astronomy or classical astronomy, it comes from particle physics. It has developed in a different way, and that's why certain things in X-ray astronomy work in a different way, just because we've always done it. Some of them are better, some of them perhaps are also worse. And so I want to lead you to this point a little bit. Most of you will have seen this before, but I want to show you really what are the most important things that enter what we're going to do next. Since I'm getting older, I'll be stopping at kind of the chi-square level, because then the young guys have to do all the old Bayesian statistics and so on. But I think this is important background to know, because in some sense it only tells you how to work with this linear data model that I'm describing in more detail here. Right? The beauty of X-ray astronomy in some sense is that people have realized it is important, and therefore we have a large number of missions. We have here obviously a bit an E Rosetta and XMM with a little bit of integral background in what you just mentioned in the science interests, right? But we should not forget that we are in the very, very good situation that there is a large number of missions out there that we can work with. The beauty of the standardization, that we always work with the same type of data model, means that essentially the analysis ideas behind all of these missions are the same. Right? If you know how to work with one mission, in principle you can work with all missions, but you should still read the manuals. So the situation right now is very good. This is the mission timeline of everything that flies right now. The blue block here is everything that is X-rays. And in the future, thankfully, life will continue to be rather good until at least the mid of the 2020s. And then obviously we're all waiting for Athena in the future. What is common to most of these satellites that fly right now is the type of the detection process that we have. So since our sources are astronomical sources, this means they are incredibly faint. We usually need some way to collect the photons in the focal plane. And this is in the soft X-rays mainly done using some type of an imaging process, using some type of X-ray mirrors. Integral is mentioned here, right? There are also coded mask instruments, and there are some instruments, for example, that use concentrators like NICER, which is just really LGO mirrors, or which use just collimators, which means essentially holes that limit our field of view. Then these photons are concentrated onto a detector, which is some piece of semiconductor material or other material in which the energy of the photons is converted in an electrical signal. This conversion might be caused, for example, by the production of electron-hole pairs or something like that. And then there is the complex electronics at the end, which then converts this charge that's deposited proportional more or less to the infalling energy into an electrical signal. And that electrical signal is telemetered to ground. On ground, you do a data reduction first, which means you take all of this data, apply some filtering to it, and in the end, you get a signal out that you then analyze. Most of what we are talking about today is about these two steps here, but it is very important to understand what happens here so that you can understand where the pitfalls lie in these steps here at the end. Okay? So I present some information about this now. In imaging, let's take a quick look at how our mirrors work. On the detection side, we'll take a quick look at how semiconductor detectors work, because that's essentially what we're mainly using, what you are mainly using also here in the room. But in principle, all of the data model and so on that I described also applies to all of the other types of detectors that we have. Because most of these detectors are what we call linear detectors. So you put a signal in, and what comes out on the other hand, on the other side, has a linear relationship with what goes in. Okay? X-ray imaging is fairly simple because it does not work like this. Right? This is an optical telescope. X-rays fall in. If X-rays fall in here, they come out on the other hand, on the other side, and you just have a collimator. But you all know that if you want to concentrate X-rays in a focal point, if you want to collect the weak signal that you have concentrated in one point, such that you have a signal that's high enough that you can analyze it, you do some kind of a combination of mirrors, and in the end, you then have an image that is down here in the focal plane. Right? Mirrors are characterized by their collecting area, what is the open area of the thing, or what is the equivalent effective area or the effective area of the mirror, which means what is the size of a mirror that would reflect all of the photons. Okay? In X-ray astronomy, the problem is essentially that if you have radiation and you let radiation interact with a, say, metallic surface, you get some kind of change in the path of the light, and you all know that the change in the reflection angle here, from the infalling angle and the outgoing angle at this interface between two media, is given by Snell's law. I think he really was the guy who discovered it. Well, we should check that. I think Newton screwed it up. So, and you know that if this ratio here, which is the index of refraction, is larger than 1, then you get then you get internal reflection, and if you kind of find a way to bring the radiation back in the other direction, you have total reflection. So we need to know when we send light onto the surface, when does it bounce off to the other side. And the problem with X-rays is that they are X-rays, that is that they are very strongly penetrating. If you calculate how X-rays are reflected off the surface, what really happens is that an electromagnetic wave comes in there, it starts shaking the electrons, and then the electrons start emitting radiation and scatter this out. And, so if you have free electrons, you can show that you can calculate the index of refraction of the material here by Maxwell's relation, found by Maxwell. I don't know. We need to check that. And essentially, for free electrons, what enters here is the dielectricity constant, and for free electrons, that's essentially given by 1 over the frequency scaled with the plasma frequency here. Plugging in numbers, you find that the dielectricity constant for X-rays scales like this, and if you then plug in numbers for X-rays, you find that the critical angle from which reflection occurs is essentially 5 arc minutes times the density of the material times some other constant. What this means is that X-rays only get reflected under very shallow angles. Okay? And this is why, jump over this, this is why our mirrors look very different. Here I'm plotting the reflectivity for gold. Here's the photon energy. Here's the amount of photons that get reflected as a function of angle. And you see these angles are all in the order of arc minutes, right? So if you want to reflect, for example, photons up to 10 keV, which is really what you want because the astrophysically abundant elements go up to iron, and iron lines, the K-alpha line is at 6 keV, so you probably, when you want to do, if you want to do diagnostics, you want to go up to 10 keV. This tells you here that you need to reflect the radiation of at an angle of 0.2 to 0.4 degrees or so. You also see that the reflectivity of the mirror material that we are using is extremely energy dependent. Okay, our mirrors, if you were to translate this into optical light, our mirrors would be extremely powerful. Okay, and this would cause a lot of problems when you do spectral analysis. So the solution to this obviously was found by Walter when he was thinking about how to do X-ray microscopy. Namely, you take a hyperboloid, for example, and a paraboloid, take your paraxial radiation, and in this type of a construction, you can essentially build a mirror that has a focal length that is such that you can build a mirror system that you can put on a satellite, which means physically something like 10 to 15 meters. Okay, that's the reason why we use 2 mirrors there. The problem with this is the small collecting area, right? These mirrors only collect over a very small ring, and so you need to move many of these mirrors into each other in order to get enough collecting area such that you get a good astrophysical signal. Rule of thumb you want to remember, perhaps if you want to sell X-ray astronomy to people in other fields, the less than 1 square meter effective area of Athena, right, by far the largest X-ray telescope that our community has ever discussed and thought about building. The total reflecting area of this mirror corresponds to a 20-meter diameter normal parabolic mirror. Okay? So Athena is comparable in its optic to the ELTs. Yeah? So people ask you why it's so expensive. Well, it's so expensive because it's the same scale. We just have a better way of putting the mirror together in a small place. Yeah? So, these mirrors then produce an image, and an image of a point source will be mapped onto something that is not a point source, but it is an extended splotch on the surface of in the focal plane, which is called the point spread function. And this is a typical cut through a point spread function. Note that this is a logarithmic scale, so most of the photons here, this is for XMM by the way, most of the photons arrive here in the innermost arc seconds, but because the optics are so complicated and need so much alignment, typically on, if you want high area, your spatial resolution that is implied by the shape of the point spread function is on the order of 10, 20, 30 arc seconds. And strongly energy dependent for the reasons that the reflectivity has such a strong angular dependence. Okay, so that's the first problem. Our telescopes really are not very good optics. They have very strong astigmatism and very strong energy dependence. Okay, I once did a slight check. If you look through optical telescopes in the 1820s, we have a few at Remas Observatory. If you look through these telescopes with the old lenses, you see tons of chromatic aberration on the side. This is what an X-ray telescope looks like. Okay, so we have one telescope built by Fraunhofer in Bamberg. Fraunhofer is this really famous guy, and you would think really good optical engineer. Right? He was the best optical engineer of his generation. If you look through this telescope, you really have problems understanding what you're seeing. Yeah, because the telescope is so bad. And this telescope optically sees still better than what X-ray strongly has. Okay, that is our problem if you don't use chart. The second problem now is, now we know how photons arrive in the focal plane. The next step is now how do we detect them? Well, how does radiation interact with matter? Let's look at a semiconductor. It has a conduction band and a valence band. Conduction band and a valence band. The photon comes in, interacts with electrons in the material, and gives its energy to these electrons. In the end, the electron will get lifted into the conduction band up here, and then if you have some way to measure these electrons, you can say, hey, I have detected a photon. Or, well, I have detected something that produces charge in my medium. Okay? So, this separation here is about 1 electron volt, which means in your typical semiconductor material, optical light results in the formation of roughly 1 electron volt pair in the detectors. The problem is, obviously, if you have electrons here and a hole down there, the electron will fall down. So what you do then is you apply some kind of a voltage, and you dope your material, and you bring an N-type and a P-type semiconductor together, and this results in a field in the detector that will then drag the electrons in the holes apart from each other, and this way you can start collecting charge and really measure the charge that is deposited. Okay? So this principle here of a p-n junction in which you form electron hole pairs by X-rays, this is what an X-ray detector is all about if you use silicon or another semiconductor lab. The number of electron hole pairs is a constant of the material here. I plot here the typical material that is used for X-ray detectors. In practice, people mainly use silicon and cat-tel, or cat-zinc and tel. The reason why they use these two materials is that the nuclear charge is fairly high, so they are absorbent for X-rays, and the band gaps are okay. So if you look here at the energy produced for an electron hole pair, you find that every 3.6 eV or so produces 1 electron hole pair. So if you don't throw an optical photon onto the detector but X-rays, you immediately see here that an X-ray produces roughly 1 electron hole pair per eV divided by 4 or so, right? So if you have, say, 1000 keV, you produce 250 electrons in this one photon, and that is a charge that's large enough that if you amplify it, you can measure. Okay? That's how an X-ray detector works in principle. Okay? In practice, it's more complicated. This is a cut through one of these detectors because we want to do imaging, so we also want to measure where on the silicon did the photon arrive. The way you do this is that the X-rays come in, produce photoelectrons. These photoelectrons then are collected in potential wells that are produced by contacts that are on the outside of the medium by just applying a charge there. Photons will then end up at that location if they are produced at that location. Okay, and once we have found the electrons, we can then change these charges and move these potential wells to the side of the detector where we can read them out. Okay, there's an alternative that is not yet flying, but for example, on Athena we'll be using that, which is you might also read them out here. But right now the detectors that are flying all imply that you're moving electrons through the bulk, and that means you can also lose electrons when they move through the bulk. Okay, so whatever you do will probably, in your later analysis, will probably be spatially dependent on where the photons arrived in the first place. So we'll then read them out here, do some electronics, and out comes a number, which is often called the pulse height analyzer number. And sometimes after you apply some more magic to it, the PI, the pulse invariance number, and that number is essentially something that is more or less proportional to the charge that was deposited in the detector. Okay? So, now there are some things that are important to know, and it's also important to talk about terminology. So we've now seen a photon arrives, you produce some electrons. Usually you do an absorption in the inner shell. This produces a photoelectron, which has a fairly high energy. This photoelectron then scatters off free electrons in the semiconductor, and in the end you have this charge cloud there. And you have a charge cloud, and that is then moved towards the readout. Okay? So each photon is not detected at a single delta peak, but you have a charge cloud that has a certain size, and you measure that charge cloud. For example, here. So if you have a photon that arrives at this location, it produces a charge cloud that looks like this, and then these electrons that are in this pixel here will be detected at in this location. These photons will be detected at this location. These photons will be detected at this location. Okay? This is called now a multi-pixel type event, and so if you have typical pixel sizes which are such that the pixel size roughly is the same as the charge cloud, it's very simple to see that you can have these three types of a pattern that emerges in your data. All of the charge cloud might be detected in one pixel. We call this a single event, 2, double, triple, and quadruple. The total deposited charge then is somehow the sum over what was detected here minus whatever in your electronics design you decided to throw away on board of the satellite, because you also produce charge just by thermal noise in the detector, so there will be a lower there will be a lower threshold for the detected charge. For example, you might probably not transmit this information here if you have a simple electronics, or you talk with Konrad on how you can make this in a more complex way. Okay? So careful here. In ESA land, these are single, double, triple, and quadruple events. In NASA land, these are called grade 0, grade 1, 2, 3, 4, 5, and so on. Okay? If you talk to an American X-ray astronomer who rarely travels to Europe, as I do every now and then, you talk about singles and doubles, they'll look at you and not understand. Yes, this has happened to me in cohort. And then you need to switch over and talk about event rates, and suddenly they understand what you're talking about. Okay, so this is a problem later in the analysis because the behavior of the detectors will depend on how we move these charges through the detector. That will have an effect on the data analysis. In addition, our detector is sensitive to everything that produces electron-hole pairs, which means also charged particles that move through the detector. This is what a long closed observation looks like of, I think, this was Susanne or something like that. And you see these tracks going through your detector, and that means when you filter things, either you have to filter out all of these tracks which produce another signal that you cannot primarily distinguish from real photons. And we'll be talking about all of this background later. Now, everything produces charge clouds. For example, also optical light, right? So if you look at a bright source, for example, you might be seeing patterns like this. This was a first magnitude star that was inadvertently observed with Swift, which produces a very beautiful pictures, but it's just optical motive, okay? So you have many effects that also cause a signal, and you need to understand these effects if you want to do the data analysis. So, how do we do the data analysis? I've just given you an overview on how our detectors work. Let's now look at what we really do. Okay? In order to do that, we need to look at two things, and it often makes sense to separate them. One is we need to look at the sensitivity of the detector. That means how much signal do we get from a photon. And this is something that's related to how big is our detector, if you want, and how efficient is our measurement. And we often translate this as what's called the ARF, the ancillary response function, or as an energy-dependent area, collecting area. And we have to look at the second thing, and that is how do we map the original energy of the photon onto the electronic signal that we look at later, so either the PHA or the PI value. So where is the signal detected now? And this is called the detector response. Formally, this can all be summarized in this equation. And if you do X-ray data modeling, what you're trying to do is you try to solve this equation here. Okay? Now, what is this equation? This is what you really detect. You have some type of a count rate, events per second, or a total number of events. If you multiply this with your exposure time, this is the signal you're working with. What enters the detector is the photon flux density, which is energy dependent here. This is something like photons per square centimeter second in keV. Okay? This is the measurement. This is the astrophysics. Okay? So what we really want to do is we want to invert this equation. Now, how are these two things related to each other? Well, the photon flux arrives on the detector. Then the photon flux then we've seen that the detector, that only a certain fraction of the flux at a given energy is really detected. This is the sensitivity of the detector, or the effective area. And then whatever is then really absorbed in the detector gets then detected in a channel C here, and this is called the detector response. That describes you the probability that a photon of energy E is detected in channel C. Okay? So obviously, in order to predict how many photons you see in channel C, you need to integrate everything over all of the energies. Okay? In addition, you have a background that just gets added to this here. Okay? And all of what we are talking about in this workshop is how do we deal with this equation? How do we given n, how do we get f? Okay? So what enters these terms here? Let's start with the effective area. I've introduced mirrors, and we've seen that there is an angular-dependent reflectivity of mirrors. Here's an example for the Athena-like mission. This is about a little bit more than 1 square meter of iridium-coated Volta mirrors. This is what the effective area for these mirrors will look like. You see, it reflects very well in low energies. So here, the reflective, essentially, if a photon arrives on the detector, it will get reflected onto the focal plane. But if you go to higher energies, the reflectivity gets less and less efficient. This introduces, due to the way how photons get reflected in the mirror, strong energy-dependent changes in the reflection, okay, from the mirror material. So the mirror changes reflectivity very dramatically. Now you need some type of an optical filter because you really do not want to observe optical stars, right? We want to observe X-rays. So what you typically take is you take some kind of a reflecting thingy, for example, aluminum, you put this on a plastic foil, and then photons get absorbed in this. Also soft X-rays. This causes then this red curve here. Okay? In addition, you absorb this. You want to absorb the photons in your detector, and that means you have a piece of silicon, and that piece of silicon will absorb not all, but only some of the photons. You see here that at low energies, the effective area got reduced a bit. This is just because on the top of your silicon detector, you have some electronics plus silicon oxide, and the electron hole pairs that are produced there are not detected. Okay? So you reduce the effective area here. On the high energy side, you see that the effective area really drops quite a lot. This is just because X-rays are strongly penetrating. Your silicon might be not thick enough to absorb all of the high energetic photons. And so in the end, your effective area will try to be like this. Okay? This is the first ingredient.
Sorry, can I just ask a short question? You said that the mirror is a 1 meter square area.
Roughly.
But they must be more, right? Because on the soft part, you have an area effective area that is larger than 10 to 4.
Yes, the reason why I said this is that I just took the first Athena mirror model that I found on my laptop yesterday night, and I don't know which one it was.
Okay.
So this is why it says Athena-like. Okay, but in the end, what you see, the mirror area here is fairly large, right? In the end, you end up here. I think this was the 2 square meters.
So maybe it was some physics to make the effective area larger than the area itself.
But what you see here really is, yes, you have to make the mirror area, even the effective area of the mirror has to be larger than the effective area of the system because you have these loss terms by the filters and by the detector. Yeah? So, okay. What we also see here is you're imprinting a lot of information about the detector material in your sensitivity. Okay? And this is a huge problem because I think, well, this is what keeps Konrad and others in the business. Okay? So, just for the reference, a nice plot that Buchner did a few years ago. This is what the effective areas of various missions look like. So, second thing now is we have our photon. We can calculate how many photons arrive on the detector and get absorbed there. So, the second thing is now, what is the charge that's deposited? And that's described by the response matrix. I said before, in the optical there's 1 pair per photon, and this is why in the optical you want to make long exposures. Okay? Because in the optical, with the CCD, you measure intensity. You measure how many optical photons arrived on the detector, and you want to long exposure. In the X-rays, we've seen that we collect many pairs per photon. So the collected charge is proportional to the photon energy. Okay, so if you can measure the charge from an individual photon, you can do spectroscopy. And since you also know the location, you can do imaging spectroscopy. Okay, this is what we call it. Optical astronomers, by the way, would call this multicolor photometry, because that's really what we're doing. So, how well can we determine the energy? Well, I showed you before that we can calculate the number of the pairs produced. This was just the photon energy divided by the band gap, effectively. So let's look at how much this varies. between for monoenergetic source between different photons. And the answer to this is Poisson statistics. So the uncertainty of the number of pairs that's produced will just be proportional to the square root because Poisson statistics. So in the end, we can measure the relative, well, the distribution of the pairs that are deposited in the bulk goes like 1 over the square root of the number of pairs. Okay? So, but since the number of pairs is proportional to the photon energy, what we've really just seen here is we've measured the relative energy resolution of this detector, and since the number of pairs is proportional to the energy itself, the relative energy distribution of the detector like this looks, if you do the exact equations, like this. With a correction factor, which is called the Barlow factor, which accounts for statistics. The answer then is on the order of 2% or so, which is why we really do multipolar photon. This is what a real response matrix looks like. This is a silicon detector. This is a gas proportional counter, by the way. So this is one cut through a response matrix. You take monoenergetic photons, you throw them onto the detector, and then you plot what you're measuring. Okay? The blue thing is what goes in. Black curve here is what comes out. Okay? This is very so this is more complicated than what I planned before. Okay? The width here is caused by this equation. Okay? So when we talk about the resolution, we're really talking about the width here. The delta function gets mapped onto this. Then we see this here. This is called an escape peak. You know what that is? You don't know what that is? Okay. Take bulk of material, a photon comes in, gets absorbed by a silicon atom. The absorption by the silicon atom will be mainly in the K shell. So if you plot the energy scheme for silicon, right, you have the K shell, the L shell, so the 1s, right, 2s, 2p here, and so on. Photon gets absorbed by this electron here. Okay, the electron gets knocked out, moves through the bulk of the material. Now we have a piece of silicon here, and that piece of silicon here has a free place in the 1s, the K shell. Okay? Now what happens, this is energetically a better place for an electron to be than, for example, the L shell. Okay? So what do we do? This electron here moves downwards. Result is emission of a K alpha silicon K alpha photon. Okay? So we produce another photon by the absorption event. Okay? Now there is a problem. The problem is called physics. And physics is always, right, solves everything, but also causes more problems. And this is related to the fact that if you plot the cross-section for any material, it will roughly look like this. So the photoabsorption cross-section for material for atoms is proportional to e to the minus q, e to the minus 3, right? It's nothing more than high energetic radiation. It's more penetrating than low energetic radiation. This jump here is the K edge. So this is the energy where incoming photons have enough energy to knock out the electron. Okay? So if you have an energy that's above the K edge, the likelihood that you're absorbed by the K edge is really large. Okay? This energy here between of the K alpha photon is between, right, is less than the ionization energy for the K shell. Okay? So the K alpha photon will have an energy that's somewhere here. Make sense? Yeah. This jump here tells you that we are far more transparent than above the energy, okay? So the likelihood that the fluorescence photon there's a likelihood that this fluorescence photon can leave the detector, which means it's not going to get absorbed, which means it's not going to deposit energy. Okay? So a certain fraction, a few percent or less, of these photons will end up here, because this is all of the photons where the silicon fluorescence could leave the detector. That's why this escaped the detector. That's why this is called the escape peak. Okay? Then there's another feature here. This is called the quantum shelf. Why? Because there's a process that was perhaps discovered by Buchner. Careful here. And that means a photon can interact with and do inelastic scattering of electrons, right? And so this inelastic scattering might result in just enough phonons that you don't produce electron-hole pairs before you get absorbed. Okay? And so your photon scatters once or twice before it gets absorbed, so it loses some energy. You do not measure this energy because it just goes into scattering and that produces. Okay? Now, this is what a simplified response matrix looks like. This is an early Rosetta measurement for 5.9 keV photons and 6.5 keV photons came in. And you see, for example, here that there is the silicon escape peak. This is exactly what I just described. Now you measure it for Rosetta. I mentioned before, this is a small effect. Okay, this is a linear scale, this is a logarithmic scale. But if you want to do high precision spectroscopy, you better know what's going on here. Okay? This is a verse example just to show to you a little bit better what a response matrix looks like. What I'm plotting here is on the x-axis the energy of the photon that arrives at the photon, and then that arrives at this given energy. And on the y-axis is the channel value. The darkness describes the probability that you get detected in this channel. So, for example, here for the 10 keV photon, you might be detected somewhere here around 6 keV or around 10 keV. Okay? What this tells you is that if you're studying something here at this energy, for example, you'd better know what happens to 10 keV, because otherwise you can't predict what you're going to see. Okay. This, in sum, is why X-ray astronomy is complicated. Okay, this figure. So, this is a slide I put in there because I didn't know where I should put it in there. So far, what we've seen is, in our answers, that there is a linear, what I've described right now is this equation. Okay? Photons arrive, this is the effective area, this is the response we detect. This is not always the case, because, especially for bright sources, you might not be able to find a detector that's fast enough to detect charge from any given individual photon, but your detector might also detect charge from 2 photons during one readout cycle, and this is called pileup. Okay, so if you look at a brighter source, rule of thumb right now for Athena in 10 years, a brighter source is essentially most of what Rosetta will detect, roughly. And everything that Rosetta detected will be a bright source. Then you get what's called pileup, and that means, like, for example, 2 photons arriving in the same pixel in the same readout cycle, so you only detect the sum of the charges, or 2 photons arriving in neighboring pixels, which look like a double event. This is called energy pileup and pattern pileup, and effectively what this is this is where the model that I just talked about breaks down. You can take care of this, we can perhaps talk a little bit about this, but in principle this is important. Okay, so how do we things now? Do we do things now in practice? Statistics will start in a few minutes. This is the equation we have to solve, and we have to invert. If you look at this product here, you see it's an extremely energy-dependent matrix that also has a side arm. Okay? If you listen to your linear algebra lectures 50 years ago, first semester, you hated them, and that's why you went into observations rather than theory. Somebody will have told you that these matrices cannot be inverted, cannot numerically be inverted. Okay? So you cannot take this piece here and solve this equation in a numerically stable way and f of e out. Okay? You can do that when you have a relatively nice diagonal matrix. And this is why if you do optical astronomy, you often can just multiply with a filter response and then apply a conversion factor, and you get something out that almost looks like photon flux. Okay? Here, we mathematically cannot go from the measured value back to f of e in a unique way. So, what did we do? The solution is we take this matrix here, we discreticize it in some way. There's a naive way and an intelligent way. The naive way is essentially you think back to your, again, to your first year math, and you say, oh my god, this thing is an integral f of e dE is approximately the sum of f of ei times delta ei, right? Then you suddenly get a matrix out of this, and if you do this for each channel value here, you get a matrix equation that looks like this. Okay? This again tells you how, knowing a certain flux value, you can predict what the total source counts will look like. Okay? And then you take this thing and you put it in some kind, and this tells you now if I know A and R, if I know the response matrix and the effective area, I can calculate what the predicted flux should look like by just doing the sum and adding the background. Okay? And then you compare this with your real data. And you use some kind of a statistics, some kind of a measure of goodness on how well this prediction compares to the data. Okay? And then you will usually have a parameter vector x here. And you vary that parameter vector until you get agreement. And then you're happy because you fit your first little power law to the data. Okay? This is effectively what we do when we do X-ray astronomy. So I will stop here. The problems start really when you think about what this fit statistics is. We will see that this fit statistics is not, in many cases, not a good way of doing things. We will see that there are more complex values. We'll see that because our matrix looks so bad, usually our solution is not unique. You can have many different models that give the same answer. And one of the things that we have to look at is how can we decide which one is better? The answer to this here in this workshop will mainly be there are really nice ways of doing that. We will show you techniques, but the answer is also, you really need a physics degree for this because even with these methods, often you also need to think about whether what you see makes physical sense. Okay? So that's the rest. That's the rest of the workshop now to go into the nitty-gritty details. If you want to know more, there are nice books, there are nice web pages. I recommend this one. This is written by me. But it turns out there really is not a modern X-ray astronomy book, for example. If you are interested in more of these backgrounds, because you come from another field or you're from a university where X-ray astronomy is not taught, which I think is essentially most universities in Germany with the exception of 2 or so, there are like 1,200 pages of X-ray astronomy slides there. You've seen a few of them. Thank you very much. Are there questions?
Do you need to cool your detectors?
Yes.
How low?
That depends on the detector material. The rule of thumb is low enough that thermal noise is that you reduce thermal noise so that electron hole pairs can't be produced. On the other hand, if you're cooling by too much, you reduce the performance of the detector again. And the reason for that has to do with charge transfer efficiency, European word, or charge transfer inefficiency, American word, which tells you something about psychology. Right, so in other words, I deposit my charge here, and if I have an old detector where I need to shift charge to the side of the detector, there are traps and electrons get lost. Okay? So if I deposit a charge here from the far away from the radar, or here, some of the electrons get hidden in these traps. Now, many of these traps are just small little problems in the silicon bulk, and so these electrons can be thermally re-emitted again and then moved back out. Okay? So if you are too cold, all of these electrons get lost. Okay? So you try to find an optimal temperature where the charge transfer efficiency is optimal. This also causes problems, by the way, when you look at light sources. I like to look at sources with signal, so which have like 500-600 counts per second. And there, for example, you often see that we can move so many electrons through the silicon bulk that many of these small traps are filled. So the efficiency of moving charge through the detector goes up, so the charge transfer efficiency increases. That's something that's not really contained in these models.
What are the numbers?
What do we do in Euro zeta? Minus 195. Minus 100, right? So.
Is it a limiting factor for lifetime of satellite? I mean, it's a big question.
No. No. You don't need coolant. You can do that passively. Further questions?
Can you remind me how to convert the PHA values to the PI values?
Okay. Yes. So I'll be using both of these terms interchangeably. I don't like the concept of PI values, but they make sense. Effectively, what you try to do is you try to model things like the CTE value that causes a shift in your spectrum. Okay? So what you measure is the PHA value, and then you try to bring this onto a common grid for, say, all detector locations. And that's what's called the pulse invariant value. You might also know, for example, that your detector has nonlinearities in the amplification, okay, which are such that you can correct them before you go to this linear equation. Okay? And that's usually what's called the PI value. That's part of the calibration, and it's an often overlooked source of systematic uncertainties in what we're doing here. If not, now come the equations.
Right. Could you leave this slide on for a second? And, So Joern just showed you this equation and its discretized form. And so what we have on the left side is the number of counts. And on the right side we have something which we can summarize as some response matrix, where I put in also the exposure time, the area, and the delta E. And then on the right you have your flux, your actual astrophysical concept. And I will just abstract everything that he says into this, and then look forward how we deal with this statistically. That we have here a number of counts, and here we have a spectrum. Okay, let me switch to mine. Right. So let's start simple, and let's just look at one single energy bit. So one channel of our detector detects something, and we can predict with our model, assuming some astrophysical spectrum, we can predict the number of counts that we should detect, right? And now, coming from the statistics side, I'll try to explain basically count statistics, and I will then try to merge the two concepts and how they connect. So the simplest process that is applicable here is a coin flip. So you have some statistical process, some coin flip, for example, and you have either a hit or a miss. Right? So you have two possible outcomes, and you have outcome 0 with probability p, and outcome 1 with probability 1 minus p. Okay? And you might have this in one scenario, and then in another scenario, and so forth. And what I'm talking about here is, for example, one day you might, elections are once every 4 years or something like that, and then you ask, is on that particular day an election that might have some probability? Okay? You might fill or not fill that day. And then if we go beyond this and say, well, I try not just once, but n times, so I have this whole sequence, I have n chances, each with probability p. What is the probability that the first k will be successful, and the rest of them will be not successful? Okay? So the probability, we would just multiply, we have p, k times, and 1 minus p the rest of the times. Okay? But that's if we order it such that the first k were successful and the other were not successful. Right? So if we then ask what if any of them, in total we have k successful, but we don't care about the order, then comes the binomial factor here that accounts for these multiple options, but you see the second part of the formula is the same. And that's called binomial distribution. So you have n tries, first k are successful. Then, if you make these tries smaller and smaller, you win finer in time or whatever your axis is, but still the number of events, so the rate, the success rate, is some finite number, then you're getting into this approximation, which is called the Poisson distribution. And this is basically always valid when we will deal with our data. And then this formula becomes that formula. I will spare you the derivation, but we can look at how that distribution looks like. And here, lambda is always the success rate on average, and k is the actual number of events that you successfully have. So let's look at that distribution. This is what it looks like for an expected rate of one event. The probability that you actually see k events has this kind of distribution. For 4, it's the violet one, and for 10 events, it's the blue one. Okay? So a couple of properties of this Poisson distribution. It's defined at integer values. So it's not defined at 0.5 events, because it doesn't make sense. That's k, lambda, this rate is a real value. It can be anything, but positive, so it can be 1.1 because it's an average rate. And it's also the mean and the variance. Variance is the square of the standard deviation of that distribution. So it tells you the location and the spread. This distribution is also asymmetric. Integer I already already said, and it's only defined in positive values because you can only have 0 or a positive number of events. And this asymmetry also causes quite a few of these inference issues that we'll talk about later. If you scale, so if you take this and you multiply it by 4, you also see that that's a distribution. If you just multiply it and shift it over, it changes shape, so it's not shape invariant. Interestingly enough, also, if you have one Poisson process, have some process that produces a certain number of events per observation, another process that produces a certain number of events, and then you take the events and you add them together, the distribution you have is again a Poisson distribution. There's a theorem about this, and this is the reason that we can add Poisson processes. This is the reason we can look at variable point sources and look at the average spectrum, because then we're looking at the averaged rates. Otherwise, you couldn't add those together. If you subtract one Poisson process from another Poisson process, you get something which is called a scalar distribution, which, as far as I know, no one has used in X-ray astronomy. And also these now I'm trying to connect this to X-ray astronomy. These count processes happen when you sample photons, for example, or in electronics when you shock noise. And here you see an optical image with relatively low exposure, and you see this granularity here. That's because you have a discrete number of photons, and you get this kind of Poisson statistics in there as well. Now let's compare this to a Gaussian distribution. The Gaussian distribution has the mean and the variance, and if we set both of those, we could set both of those to lambda, the average conf rate, or we could set both of those to k, which is the number of events we have, because we don't know lambda. This is actually what we're trying to infer, the photon flux out there in the universe. The other difference Poisson and Gaussian is that the Gaussian distribution is a real distribution, and it can be negative. So you could describe that you have a negative number of events, which doesn't really make sense. So let's look at how they diverge. So here, what I'm plotting is in blue, I plot this formula, which is the Poisson probability to get k events under a rate lambda. And I assume I have k, because this is how many photons I detected. And I don't know lambda, so I will plot lambda here, which is the expected number of counts. And this we also call the likelihood, which is the probability to have k events under this model. Okay? So if I have one count, the Poisson distribution looks like this. It looks very asymmetric. If I take a Gaussian distribution and compare it to this number of counts, the shapes look like this. I increase to 5 counts. Again, they look quite different. And the difference is the Poisson distribution has a more permissive tail at the low end, which you can interpret that if you expect only few counts, the Poisson distribution can make one count, or can make a few counts more easily than you would describe with a Gaussian distribution. And this comes from the asymmetry of the distribution. And you have the other way around here at the high tail end. And one consequence of this is if you have a number of counts and you try to infer some luminosity of the source, if you take this approximation, you might underestimate how faint the source could be. Increasing the number of counts, we get to 10 counts, still you have the difference, 20 counts, and then at 40 counts, they somewhat look similar. The green curve I haven't talked about is if you take for the width of that Gaussian, you take this curve So the bottom line, the Gaussian distribution and the Poisson distribution do look different. If you want to do it right, because we have counted the right way to do it is model the Poisson distribution. Historically, people have used the Gaussian because it's faster to evaluate, at least on previous generations of computers. And I guess there's also some familiarity in terms of tools coming from optical astronomy. But I don't really see a reason these days to approximate anything with the Gaussian.
I would add that, especially the history thing, that an argument also comes that the interpretability of the distance metric of a Gaussian, which is just, the square distance, people feel that they know how far away a counter is from a model. But as you should just show that that's very misleading.
Okay, so if we write down the two probability distributions of a Poisson and Gaussian, this is the formula. And now we do a magic trick, which is take the logarithm and multiply by -2. And then we have -2 times the log likelihood is lambda comes from the exponent down, and with the -2 it becomes +2 lambda. Lambda to the k. If I take the logarithm, I get k log lambda, and I get the -2 here. And we call this thing, and we get some constants, which we don't care about because the number of number of events is constant. We care for solving lambda. And this thing, depending on what constants are added there, is called C-stat or cache or pastoral statistics. And it's nothing but that Poisson process likelihood with -2 times the logarithm. Nothing magic about it. And if we do the same for the Gaussian, we have the Gaussian probability distribution to have a value of x measured from an expected mean and dispersion. We take -2 times the log. We get this term stays over, goes -2, and the log takes care of this. And this is what people call chi-square.
Johannes,
Yeah.
could you, almost in general, explain what exactly you mean by likelihood in the statistics context for the people who are less statistics background?
So the likelihood, again, is just the probability to produce this data, assuming we have a model with parameters and fix these parameters. How often will this model produce this data set? How frequently? What is its tendency to produce this data? I actually have another slide on that. And when people talk about chi-square minimization or minimizing C-stat, what they really mean is they maximize these likelihoods. They want to find the parameters or the model that tends to produce this kind of data. So it's kind of prone to making this data that you actually have. And this is the same. I'm going to take this, and I just have another data set, another bin, and I add those together. And why does that make sense? Because if I look in likelihoods, I have one probability and I multiply it with another probability. That just means the model has to be true in this data set and it has to be true in that data set, and that logical AND is a multiplication here, and in log space it's a summation. For a Gaussian probability, I again multiply those two, and in log space I have this plus this, which is exactly the chi-square sum. This is where it comes from, and this is the reason why people do the -2 log also in the Poisson. But yeah, all it does is trying to maximize these likelihoods. Okay, now coming to this approximation again, now we have these multiple bins, each with the response, and it's discretized. So here is the response matrix. Here are the number of counts in each detector bin, which we actually detected. And what we can apply here onto that matrix is our SAE of our astrophysical source. And then we can write it as the expected number in that bin is just that matrix multiplication of that flux vector onto that matrix. And then the Poisson likelihood is that formula. I write it now vectorized, but you don't really have to know about it. But it's basically here we're comparing that this expected rate matches this number of counts, this matches that, and so forth. And then we get a probability of. And just to keep in mind, what we have here is a flux which has ergs per second per centimeter squared per kV. And here we have number of photons per centimeter squared per second per kV. And then we multiply by the width of this energy, by the observing time, and by the detector area. So we actually get the expected number of counts and compare that to the number of counts. So the units make sense in that space. Okay, so I would like to move on to dealing with backgrounds, unless there are some urgent questions right there. But I will come back to the likelihoods a little bit later when we go into how we actually do the fitting. Urgent question? No? Okay. So in point sources, what we usually have is we have a source that we're interested in, and we get counts from that region. But as Joern showed before, we also have backgrounds to deal with, and it's very common to take some background region which is somewhere nearby and try to estimate the strength and the shape of that background. So you get a spectrum here, and you get a spectrum somewhere else, and we can again write them like this. And what we're also going to assume right now is that the background is, because you take it close by and you take it at the same time, that this background region is somewhat representative of your source region. So you have a similar time and a similar area maybe, where you multiply by the area ratio. And then what you have in the background region is you have your background flux, you multiply it with the response, and you get your background contribution, a background count rate. And for the source region, you have a background and your source go through the response, and you have it in the detector. And the statistics are exactly the same, so you add flux and flux with the response, and you have the source. Or for the background, you just have the background. And for the CSAT, for the Poisson, you just add again these terms together, and that's what we would call the simultaneous fit. Now, this might not be true, because your background might not go through the response. It might not go through all your mirrors, but just come in from the side as a proton background. And you might not really care about your astrophysical, or the meaning, the physical meaning of that background. You might just care about what happens on the detector level. So simplifying this a bit, you could also describe it just on the detector level, and then you try to infer how much of this contribution is leaking into this part. Okay? So what are the strategies to deal with now that we have source and background? Well, in optical astronomy, you would have source and background being Gaussian, and then you measure the background, and you subtract the two, and again you have a Gaussian process. What we have here are both the background and the source are Poisson. If you have extremely high counts in every single spectral bin, in the background and in the source, you could subtract them with the Gaussian approximation. assuming you propagate also the variance that you introduced there. Or you subtract them and model them with the scalar distribution. Nobody does this. Or you do the right thing and model both of them as Poisson distributions. And if you choose that option, you have three strategies. Well, three now. One is you look at each bin individually and take the background counts in each bin and try to estimate the rate. And we will hear later about that. Or you try to find some model that describes how this background behaves on the detector level, either in counts or you try to make some physical model for it, or semi-physical. And then if you have these kind of models, you can simultaneously fit both the background and the source, or you try to fit the background first and then keep that fixed and use that background shape, transfer it over to the source, and add its contribution to the source contribution. Okay? So this is the background for Rosita, and I'm not an expert on the different contributions from various different effects, but this is what I found here. So one contribution is diffuse emission, for example, from the hot local bubble, galactic halo, galactic disk. So those make I think these components. And then you have a cosmic X-ray background, which is, if you look out in the sky, you always, there's a nice photo upstairs of the moon, which kind of blocks this background, and next to it you see more counts, which are these unresolved AGN, which give you basically a flat spectrum with an index of -1, I think. And then on top of that, you have the high energy particle background, which just bombards your detector, and that's fairly flat. And the sum of this is what makes up the background. What other people have done is try to model each of these components physically. And this is a model for NuSTAR, and the motivation behind this is if you have your exposure and you're looking at an extended source, you might not be able to put a background region close to your source because there is no region that is very clean. So you have to take a background region somewhat far away and kind of extrapolate how would that background behavior change over your detector. And if you understand these components, then you can do that. And I think we will hear a bit more about this tomorrow, how to analyze extended sources with backgrounds. The other option is to just empirically model backgrounds. So you have here your background region spectrum. Maybe you put just a broken power law and some Gaussians on top of that. And then you say, okay, well, I assume the background is well described by this, and then you transfer this model, scale it by the area ratio, and add it to your source contribution. The benefits of doing this kind of empirical background modeling, is that you can add physical information, and you add that it's smooth from one bin to the next, so that decreases the uncertainty. And in this case, you can also have background bins where the number of counts is actually 0. Because of the smoothness, one bin informs the next bin. There's no problem with the Poisson probability of having 0 counts. The drawbacks are that you have to find this model and you have to fit it, and it shouldn't go off into the wrong location. And yeah, and if the fit is poor, that will affect your source fit. Here's another approach that we published to find these background models automatically. So what we did there is to go to some telescope archives and look at, they already observed so many point sources, and they have background regions for each of those point sources, so maybe we can automatically learn what these backgrounds look like. And so what we did was take thousands of those sources, take their background just on a detector level and decompose them into principal component analysis. So the black curve here is the average background shape. And then you have the first, second, and third principal component, which are the different shapes that typically deform the background. So typically you have some combinations, some linear combinations of these shapes. And now with this you have a parametric model that you could fit to any individual background and describe it well for this particular detector. And there's another approach that Michael will talk about in a minute, which is to estimate the background in each individual bin, which is, by the way, what XSpec does by default. And that has some pros and cons. The pros are you don't need this kind of model specification, but the cons are that you don't assume that one bin knows about the next one. So you get also larger uncertainties. And it also doesn't work with zero bins, zero counts in one bin, because then it cannot estimate the rate. Okay, so coming back to the issue of likelihoods, just check something. Yeah, actually, do you want to jump in at this point?
Yeah, how much time do we have before the break?
I think we have half an hour, 45 minutes. Are there questions? Just interrupt as well. I mean, it doesn't have to be this long. Yeah.
How okay, like more science, how smooth or how varied is background? Is it relatively homogenized or is it really varying a lot across the sky?
Across the sky.
Of course, we look at the galaxy often, it's different, but in general, for far.
Well, so you have these different components. Well, one source of background I didn't actually explicitly mention, which is inside the instrument, because your instrument is made out of some metals, they produce lines, and also you have these structures that hold up the instrument, and they block sometimes the external background and sometimes not. So actually, if you look at the detector image itself, it also varies on the position because of that. So I would say it can vary substantially because of that, and not because of the sky itself. Also, it's time variable because of solar wind, and yeah, it's not an easy topic. Often you have to look how sensitive you are to your background choices. But actually, I'm sure there are people in this room who know more about this, and I would be happy if they say something either today or tomorrow.
Okay, cool. So I'm Michael. I don't actually work with X-ray data. I work with higher energies, but it's still technically X-rays because gamma rays are defined as nuclear photons. But so we're all X-ray astronomers. But I don't work with imaging detectors very much, typically non-imaging detectors. But I'll talk about, for now, how to deal with source plus background. So, source plus background in the statistics that you typically find in XSpec, and how to model these sources. So, again, I typically work with time series. So, I would define my background region as being over here, whereas with an image, you would have your background region here, and then your source region here. Now, we won't talk about this part real quick, how to model this, but we would do it in a different way. But in both cases, I could extract my background from an off-source region. And so if I think that my source is here, like this spike, I would say that this is my off-source region, and the same thing with the image. which would mean that my background I would take as a measurement, which means it's Poisson distributed. So in that case, I have this likelihood, which I'll talk more about what a likelihood is, but it's the probability of my data given my model. And here, this is, since both my observation, when I call it observation, would be source plus background, and my background are Poisson distributed, the appropriate likelihood is a joint distribution between the between the total model, source, the source plus background, and just the background. And so we can look at what each of these terms are. This is my model rate, so this would be what would be emitting from my source. This is my background rate, which would be just the background. Added together, this would be what should be predicted to be producing the emission that I see. These are the total counts in the observation, and this is the background counts in the observation. So this is the appropriate likelihood to use for these types of observations. When you have Poisson background and Poisson observation. However, as Johannes was saying, we don't always have access to a background model. And this is where this idea of WSTAT came about. And so what you can do, and I'm a diehard Bayesian, so I would not do this, but it's one way to get around the problem, is that you can pre-maximize or profile the likelihood before you do the fit, which means that you can go ahead and optimize this equation by breaking up each spectral bin, take and put a parameter that's piecewise discontinuous, and estimate what those parameters would be at the maximum of the likelihood, which just means that you maximize this equation for each of these B sub i's, the background model rate. Once you do this, you can go back and solve a quadratic equation for what these B sub I should be in terms of the other parameters, and you will arrive at having these F sub i's, which are functions of now your source, your expected source rate, as well as your observed background and total observation data. So this is just simply a profile likelihood, which just means that I've removed the dependence of the background model directly. However, we have added now, if you have 128 bins like we have in GBM, you've now added 128 parameters to your model, which means that it becomes very flexible. And since we didn't assume a continuous model, this means these bins can vary next to each other discontinuously. And what happens is, if you have 0 counts in a bin, you have no information about, or in a background bin, in your background observation, you have no information about what the actual rate is. And so you need to rebin your spectrum so that you have at least one count in each spectral background bin. And if you don't, so there's a great study online done by Johannes, where he looked at the bias in these profile likelihoods. And what you see here is the difference, the true rate is, or the true observation should be this green histogram we went through and simulated doing a bunch of spectral fits. And if you don't have, the more and more you rebin, the more accurate that this estimation of the profile works out to be. So I encourage you to go to this link. We shouldn't go through it here if you're interested, but if you're using WSTAT or CSTAT, or we still call it CSTAT in GBM, then you need to make sure that you rebin your spectrum to have at least one count in your background observation. It's better to do it at 5, but it depends on your resolution and what you want to do. Now, there is another way, which I won't go into, is that you could do a Bayesian fit and actually just marginalize over these parameters. It removes a little bit of the dependence on computationally expensive, and you need a very powerful sampler to deal with these 100 or however many spectral bands you have. Now, if you're doing instead just time series analysis, there's another way that you can model your background. Instead of just taking an observation off source, you can, what we do in GBM, so doing time series analysis with another instrument, is that you can fit a model in time. We do this like fit a polynomial to each spectral bin in time, and we get an estimation of the background under the source. Once we fit that polynomial on the off-source regions, we can then go and integrate this polynomial expected rate and get estimated background counts. But since this is coming from a fit, the distribution of those counts is no longer Poisson. Now, you'll see in papers that people will take this technique and then use Poisson distributed counts estimated from the background model, but this makes no sense because whenever you do a fit, if you do Gaussian error propagation, your future expected rates are going to be Gaussian distributed. So this has a couple of advantages. One thing, we're leveraging the time information on either side of this time series to help bring down the uncertainty in our background. So we're modeling this temporal uncertainty. If I were to just go in and grab some Poisson counts, there's no information about the fact that maybe this is a smooth varying background. So in general, the estimates of the background in this region will be a little bit better, tighter. In that case, we have to basically form another joint likelihood. And the only difference is the total observation is Poisson, but the background part is Gaussian distributed, with errors estimated from propagating this temporal model that we fit into the fit. And so this one is called PG-stat, which a lot of you, if you are doing X-ray imaging, you may be unfamiliar with, but you do time series analysis with non-imaging detectors. This is typically the profile likelihood, or the likelihood you want to use. Once again, you can go through and you can profile out all these background parameters and get something very similar to W-stat, but it has the same fragility that W-stat has, that you need to have at least one background count per bit. So I didn't say anything about subtraction, and that's because you do not subtract Poisson rates from each other and then try to fit them. We don't have to. As Johannes pointed out, that if you were to do this, you get something called a scale and distribution. If you have Poisson, I don't know what it is for Gaussian Poisson. I have actually seen it used one time for lunar prospector data, where they were trying to model search for water, and they had a Poisson background and a Poisson source for gamma rays coming up off of the surface of the moon. And they used a scale and distribution. The problem with the scale and distribution, it's a very fragile estimator. It's not very sensitive. It's basically a very peaked Gaussian with very wide tails. That's sort of what it looks like. But it's not really a good estimator for trying to figure out what's going on in the data, and it's fragile. We can go ahead and do the full joint model. And you should never, ever use background subtracted data with a Gaussian likelihood. It puts way too much probability density around the peak of the background subtracted data. So you should stay away from that. So while we're talking about backgrounds, I just wanted to add something in that I thought about, which is with significance. The significance of a source rate in the presence of a background. We'll just stick for now to the Poisson case. So, does anyone know which of these formula is the proper signal to noise formula? Alpha here is the ratio of the time on the off observation to the on observation. anyone use these formula to compute the significance of a source in the presence of background? So, of course, the answer is all of these are incorrect. I've used, I think I've probably used this one here back in undergrad as well. So, these you'll even find these in some statistics books, and especially astronomy statistics books. That they'll point to this formula, which is extremely wrong, or this formula here.
Well, it is wrong in this context. It's not wrong in general.
It's wrong in the Poisson case. Yeah. It depends. Yeah, you can get it if you have Gaussian. If you want to talk about the ratio of Gaussians or something like that, it's fine. But a lot like this estimator here and this estimator here, they actually don't even have Poisson properties. These are closer, but I'll show you in a second where they fail. So this was figured out in 1983 by Lee and Ma. This is a really amazing paper. They go through the derivation of actually how you should compute significance when you have Poisson, an off-source Poisson measurement and an on-source Poisson measurement. And the correct answer, well, I'll show you in a moment. I just like to use their plots because there's these wonderful 1980s hand-drawn plots. But here, the solid line is the correct relation between significance and probability. And all these things that are falling off of the curve are just from those different, they did Monte Carlo experiments with those different significance formula. And you see that even in the presence of a very high number of counts, these formula are extremely wrong. And so if you use them to estimate signal to noise, you will, or signal to noise or significance, you will get an extremely wrong answer. Now, there's one that seems to fall along this curve. And as we'll talk about later in more detail, it comes from using the likelihood ratio, which is the likelihood ratio of background to background plus source. And so they go through and they derive this likelihood ratio, which is quite simple, and then which we'll talk about in much more detail, they derive a significance estimator that basically actually maps significance to probability. So make sure when you have backgrounds that you're using the proper formula for estimating the significance. Now that, I will let Johannes take back over.
Do you want to maybe say what's the difference between significance and probability, and what the probability of significance?
Right, and we'll get more into detail with this later. Typically when we say something is a 4 sigma result or a 3 sigma result or whatever, what that means is it's the chance probability that we're wrong. So 5 sigma is what, 10 to the minus 5? I always get these wrong because I hate significance. But the point is you want to compute, I'll get a lot more into this when we talk about likelihood ratios. You want to map from a number, and we use sigma because we all think in Gaussians, to a probability, right? For Gaussian, this is well defined. When we break away from any Gaussian assumptions, this type of relation falls apart most of the time. And that's what's happening with those other signal-to-noise estimators or significance estimators, is that the mapping from something we call a sigma to a probability is not correct. And we'll talk about that when we go through Wilms' theorem. Are there any questions? Did I scare you? I've used the incorrect formulas and a couple of things myself. But they can be really bad, and when you go through and correct them, there's an even more recent version of this paper that includes when you have the case of the Gaussian background, and they did a Jochen and Dennerl again, did a really extensive study of how fragile these estimators are when you use the incorrect ones.
I got a question. So you said in the time series analysis you made the background Gaussian. Did I get that correctly?
Right. Well, you don't make the background Gaussian. What you do is you model the background. So whenever you've done a previous fit, all right? And you want to use that result in the maximum likelihood case. And you want to use that result in future. You have to do, for a future experiment or future measurement, you have to do error propagation. And whenever you do error propagation in the Gaussian sense, or in the maximum likelihood sense, you always have to assume, because this is the key assumption of maximum likelihood estimation, that those errors are distributed Gaussian and are small. And then you have to do Gaussian error propagation. So whenever you're using information from previous fit that is done with maximum likelihood estimation, the errors on, or the uncertainty on those future quantities are going to be Gaussian.
Okay. So if you do that, do you need like a minimum amount of counts or so?
For fitting the polynomial?
Yeah.
Well, I mean, so that's just an example. Like, yeah, well, you would have to fit that if it's Poisson data. You would have to fit it with the Poisson likelihood. So we'll get into this more again once we get into some basic statistics. There's a difference between the likelihood you use and the uncertainty on the quantities you estimate. Right? So you can have a Poisson likelihood to fit this thing in time, but if you do it with maximum likelihood, the uncertainties on the parameters, for example, of this polynomial are Gaussian, are assumed to be Gaussian.
Thanks. For this formula, is there an assumption that, this background dominated noise?
It doesn't. It doesn't really matter. Here, it's just. I mean, if it's background dominated, right? You see that the significance will go down. So this is just the number of counts you have on your observation, so which could include your source plus your background. And this is the number of counts you have off. This is the ratio of the exposure times. This is 2.
No, I mean, it's not detector noise dominated.
It's not detector. It's just noise. There's no specification of the physical source. Right? You can just have static. Static in your detector, I suppose, and that is measured on top of your source as well.
So one very often can make the assumption, but it's an assumption, that these noise components are also due to counting processes, and that's why one uses this Poisson assumption. Okay? Not always true. For example, if you have backgrounds that are statistically connected to each other, you can't make that assumption. But usually, you close your eyes and think of England kind of usually are doing a good job by assuming that it's Poisson when you work in these things. So that it comes to count, and that's why you just said, all my backgrounds better be Poisson.
You can extend it. This has been extended now to Poisson plus Gaussian as well. And even the Poisson assumption is also probably a bit fragile. There are things called over-dispersed Poisson distributions which free the mean from the variance. So in a Poisson distribution, your mean and variance are tied by definition. There are generalizations of the Poisson distribution, and in general, if you read statistics literature, they agree that nothing in the universe is really Poisson when you're taking data. But none of this has been derived for X-ray statistics, and it probably should be done, but it probably changes the estimation of these things very little. Cool.
So the reason why we go into these details is because we want to let you know that what your tools that you will actually use do by default, and expect in particular uses WStat, which is what Michael was talking about first, this per bin estimates. That's what it does by default, and you should think very hard about whether this is what you actually wanted to do. And then PGStat is the one with the Gaussian background, which was the other thing he was talking about. So you might want to think, do you want to, in each individual bin, you want these assumptions, or you want to treat the background with a dedicated background model. Okay, so let's revisit a little bit what likelihoods are and why we want to use them. So again, the likelihoods are probability to have a certain number of counts, assuming, given that we have a model with some parameters for the source, and assuming we have a response matrix and some shape of the background. So it's if you have higher likelihood values, the model under these parameters often makes these data. It tends to make this data. If you have lower likelihood values, it less frequently produces these data. And likelihoods, as I said before, if you take -2 times the logarithm of them, you end up with these, what we call C-stat and chi-square. So, but if you talk to someone else outside of X-ray astronomy, you talk to someone doing optical astronomy, or maybe even to someone doing statistics, they will not understand what you mean. I minimize my chi-square maybe, or I minimize my C-stat. But talking about likelihoods, that's a more universal language. Again, the likelihood is the frequency of producing some data, so you can write it as a probability to make some data, assuming this model. It's kind of a prediction. And it's a function. It's defined, you evaluate it for some data at some parameter values. It's not a probability density. It doesn't take a range, or it doesn't give you a region of data or a region of parameters. It just tells you, assuming all of these data, assuming all of these parameters, that's how often this process makes sense. What do we want in the end? What do we want to measure? In the end, what we would like to have is a tool that tells us is some parameter range of some physical parameters like luminosity or temperature or some other physical quantities that we're interested in. What are the allowed ranges? How well can we constrain these, right? So what are the parameter ranges allowed or probable given our observation? So what we actually want is the probability of some parameter given our observation, the counts we actually detected. And we want to measure in some range of those parameters, d theta, so we actually want a probability density in that region. And you can think of it this way, the probability of some galaxy cluster to have a temperature of between 1 keV and 1.000001 keV is basically 0, right? The probability is nil because the range is so tiny. That's why we are interested in probability densities. We want, is this parameter within some range? And you can write this as a probability density, and you can think of that range as a volume, and then if you multiply the density by a volume, you can have a probability mass. And we're looking for these ranges where most of this probability mass lies, right? And what we're going to do about fitting and constraining parameters is find the regions with these high probabilities to have these parameters. And that's all we're going to talk about in parameter space exploration. Now I'm going to come to some basic derivation of how we, so you saw we actually have to, we have this already, we have this likelihood, which is just the Poisson likelihood, maybe with some background components. But we have this, but what we actually want is this the other way around. So how do we do this? And the concept is the following. It's just conditional probabilities. So you have, let's say you have some event or some concept A and some concept B. And what we're going to describe now is the probability that both A and B happen. And you can describe this either you say, well, A happened and then also B happened, or you can describe it B happened and then A also happened. So you can write it as the probability A. So you come here from the left side, and then you write the probability that B happened, but we already know A happened, so given A. Or you can write it from the other way, you write probability of B, so we say this is true, and now we ask what fraction of B is also in A. So probability of A given B. And now we rearrange a little bit, so we have, so we're looking for, let's say, this term, probability of A given B is probability of A, probability of B given A, less that, divided by probability of B. And now what you see is, what I've done is I've switched this around. On one side I have it this way, and on the other I have it the other way. And what we do now is we interpret, so this is just conditional probabilities. There's nothing magical happening so far. But the magical part is now the interpretation of this, which is that here we say this is the probability of some parameter given our model, so we just basically label them differently, is the probability of the parameter without any data, and the probability of the data given the parameter, that's our likelihood right there, we divide by the probability of the data. Okay? And now what we've done is we have what we're actually interested in and the likelihood, and we've kind of connected the two. And this is called Bayes' theorem. And the way it works is, you have here a probability distribution, here you have a probability distribution, and here you have a likelihood function. Now the difference is, this, let's say you have already probability distribution, let's say like this, and it's defined such that any interval you take, some range d theta, has some probability. Okay? That's a density. And now we take our likelihood, which is a function, okay, and we multiply the two together, which again gives us a probability density, but it's kind of skewed by this likelihood. And so what we end up with is this probability distribution. And what we've done is we've moved from one probability distribution to another distribution. And that's kind of a knowledge update. You start out with the distribution before you saw the data to a distribution after you saw the data. That's why this is called a prior distribution, and that's a posterior distribution. And the whole reason why we do it this way is because we only know how to update probability distributions densities, but here we have something that isn't a density. Now, I haven't talked much about this, but if this is a probability distribution of some parameter, then we probably want it normalized. And if you want this on the left side normalized, then the normalization is just taking this on the right side and dividing it. So we go over the whole parameter space, we integrate the thing, and if we put that integral the probability of the data, that's going to be very interesting as well for comparing models. So let me just put that out there. We started out with basically just conditional probabilities. We ended up with Bayes' theorem, which allows us to make from our data model, which is that Poisson likelihood, and some helper function, some helper probability density, which we update to then have what we actually want, which is inference over some parameters. I know this is very confusing. But now, given this context, and given that we want to probably find the regions where most of this probability mass is, we probably want to find regions where this likelihood is highest, and we probably want to find, that means we want to find where the chi-square or the c-stat is lowest. And that's where this idea comes from, that you find that you minimize c-stat or chi-square and you go to these peaks. Right? And then you want to wiggle about there and find the parameter constraints. And so there are a whole bunch of algorithms to kind of characterize the knowledge on some parameter, which I classified here into 4 categories. One is local optimization, so finding the best fit, usually called. Then you have local sampling, where we'll talk about MCMC, jumping around and exploring this distribution a bit more. Then there are global optimization algorithms, because sometimes you might just not have one solution, but multiple solutions. And you want to find, ideally, all of them. And in the end, I'll also come to global sampling algorithms, so where we try to infer the entire distribution, even if it has multiple vectors. But I think this is a good time to stop and continue after. Okay. So let's have lunch and then talk about these afterwards. Let's meet back here at 15 past. Okay? 1 hour. 15 past 1.
Can we leave the backpacks down here? Let's say,
I think it should be safe, but it will not be long.
Yeah.